Good evening, everyone. It's my great pleasure and honor to be able to introduce John Ellis. John is a British theoretical physicist who currently holds the Clerk Maxwell Professorship of Theoretical Physics at King's College in London. He obtained his PhD from Cambridge University and held postdoctoral positions at SLAC and Caltech. From 1973 to 2011, he worked at CERN, where he was the theory division leader for 6 years. His research interests focus on the phenomenological aspects of elementary particle physics and its connections with astrophysics, cosmology, and gravity. Much of his work relates directly to experiment, interpreting results of searches for new particles, and exploring the physics that could be done with future accelerators. A proposal he made in 1976 led to the discovery of the gluon in 1979, and he was one of the first to study how the Higgs boson could be produced and discovered. He has authored over 1,000 scientific papers with over 80,000 citations in total. He has been active recently in efforts to understand the Higgs particle that was discovered at CERN, comparing the properties of this particle with the predictions of the Standard Model, and using effective field theory to understand the implications of the discovery for extensions of the Standard Model, such as supersymmetry and other possible new physics, such as dark matter. He is also now studying possible future particle accelerators and experiments to measure gravitational waves. He was elected a Fellow of the Royal Society of London in 1985. He was appointed a Commander of the Order of the British Empire in 2012 for his services to science and technology. In 2015, he was elected a Foreign Fellow of the Indian National Science Academy and a foreign member of the Estonian Academy of Sciences, and he has been awarded several honorary doctorates. As you will see for yourselves today, John is a very eloquent speaker, frequently invited to give public and educational lectures on particle physics and related topics. He is also very well known for his relentless efforts to involve non-European nations and institutions in CERN scientific and technological activities. And I've had the pleasure of knowing John now for over 20 years, and it was really due to him that I first went to CERN. So it's a pleasure to have you here, John.
So thank you very much for that very kind introduction. It's a pleasure to be back in the UAE, although this is the first time I've actually visited NYUAD, as I hope to be able to return in the future. So my title is How Physics Answers Gauguin's Questions About the Universe. I'll explain in a bit more detail what Gauguin's questions are. Anyway, I'm going to be addressing those questions from the point of view of a particle physicist, and I'm going to be taking you from the Higgs boson, which Marta has already mentioned, to the dark side of the universe. So my talking points are provided by this painting by Paul Gauguin. So here we see some people on the South Sea island asking themselves some very basic questions about human beings and their place in the universe. What are we? Where do we come from? Where are we going? And I think these are truly universal questions that everybody asks at some point or another. They gaze up at the stars and they say, what the hell? And those are the questions that Gauguin is talking about here, and those are the questions that we particle physicists address from a scientific point of view. But maybe that's a different point of view from the one that Gauguin had in mind. Anyway, people often wonder, what it is that particle physicists do, and I think they somehow lose the wood for the trees. The wood is, what is a matter in the universe made of, and how did it get here? So both Marta and I have already mentioned Peter Higgs and his boson. So he proposed a theory back in 1964 for where the masses of elementary particles come from. And that's a really key ingredient in our description of the matter that fills the universe. So this is already addressing one of Gauguin's questions: what are we? And I like this picture. It shows you Peter Higgs as a relatively young man, at least relative to me, working out some details of his theory back in 1965. So as I said, I'm going to be tackling Gauguin's questions from the perspectives of a particle physicist and part-time cosmologist. So I need to translate Gauguin's questions into the language that we use in particle physics. So what are we becomes, at least for me, the question: what is matter made of? And an ancillary part of that question is, why do things weigh? And that's where Peter Higgs and his theory play a key role, as I will describe. Where do we come from? What is the origin of the matter in the universe? We believe that the answer to that question comes from processes very early in the history of the universe, shortly after the Big Bang, and I will return to that idea later on in this talk. You may have heard that in addition to the visible matter in the universe that we're all made of, there is some other invisible dark stuff in the universe. In fact, there's more dark stuff than there is visible stuff. And so that's what I was alluding to when I talked about the dark side of the universe. I wasn't talking about Darth Vader. I was talking about dark matter, perhaps also a little bit about dark energy. So where do we come from? Where are we going? That becomes the question: how does the universe evolve? How did it get started? What's been happening up to now? And what's going to happen in the future? One aspect of this question is why is the universe so big and so old? And that is a question whose answer may be related to what Peter Higgs and others did back in the 1960s. That may also provide some clue to the third Gauguin question: what is the future of the universe? As I will discuss also later on. So I've been trying to say that it's our job as particle physicists to ask these questions and hopefully provide some answers. And I should say that I discovered Gauguin's picture on a visit to Boston, just as I was a beginning research student, and I bought a copy of that painting, which I stuck up on the wall of my office as a student, just to remind me why I came into work each day. And that's still why I come into work each day. Now, I've already mentioned that the Higgs boson answers at least some of these questions, it seems. The other questions, the ones that I've outlined in green here, need new physics beyond what we currently know. So all I'm going to do in this talk is set out what we currently know, and then I'll address these questions beyond what we know. And many of these questions are addressed by experiments at the CERN Large Hadron Collider that Marta and her team are working on together with other colleagues at other UAE universities. Okay, let's just remind ourselves of what we know about the evolution of the universe. It's been expanding for about 13.8 billion years since the Big Bang. And the part that we can detect with our observatories is about 10 to the 28 centimeters across. So the first Gauguin question is, what are all those shining points of light made of in that picture? The second Gauguin question, what happened at, or at least shortly after, the Big Bang? And the third Gauguin question is, of course, what will happen in the future? Will this expansion that's been going on for so long continue ad infinitum, or will something else happen? Perhaps the universe in the future will collapse in some sort of big anti-bang, some big crunch. And that's an interesting possibility which has been raised by recent measurements at the Large Hadron Collider. Okay, so let's just remind ourselves a little bit about the early history of the universe. So as I said, it's been expanding for 13.8 billion years since the Big Bang. And when it was very young, it was also very dense, it was very hot. In fact, when the universe was less than 300,000 years old, it was so hot that atoms could not exist. And before then, instead, you had a plasma of electrons, nuclei, and photons running around. When you go back earlier in time to something like 3 minutes after the Big Bang, that's the time when atomic nuclei were formed. They were formed out of protons and neutrons. But if you go back to when the universe was less than a microsecond old, even protons and neutrons did not exist. And instead, you had another sort of primordial plasma with the constituents of protons and neutrons, the gluon that was already mentioned, quarks floating around. When you go back to when the universe was about 1 picosecond old, so that's a millionth of a second, that's when the Higgs mechanism for giving particle masses kicked in. That's when mass appeared. I'm going to be talking later about dark matter. In many theories, dark matter emerged from this primordial soup sometime between a picosecond and a microsecond after the Big Bang. And it's possible that matter itself appeared something like a picosecond after the Big Bang. But these are issues which are still open, and these are ones that we will be addressing with the LHC. So this ruler has a logarithmic scale which takes us all the way from the 10 to the plus 28 centimeters, the size of the observable universe, down to 10 to the minus 32 centimeters, which is the smallest scale that we theorists dare think about. In fact, that's the scale where we think the concepts of space and time themselves break down. And about halfway along this logarithmic scale, we have the human scale, represented here by Albert Einstein and his kid sister, about 1 meter tall, something like that. So we know, in simple terms, what Albert Einstein and his kid sister were made of. Molecules. Molecules are made of atoms. Atoms contain nuclei with clouds of electrons around them. The nuclei contain things called protons and neutrons, which, if I had been giving this talk 80 years ago, I might have said that protons and neutrons might be elementary particles. But we no longer believe that. In fact, we know that they're made up out of more fundamental things called quarks. So this is a very brief summary of what we currently understand about the structure of matter. So the astronomers who are looking out to very large distances tell us that in addition to this visible matter, there is also invisible dark matter. That, as I just mentioned, might have decoupled from the ordinary matter in the very early history of the universe. Our experiments at the LHC explore the processes that held in the very early universe directly in the laboratory. We look deep inside the atom, deep inside the proton, at the fundamental laws, the fundamental particles of matter. And the physics that we understand provides us with a symbiosis between particle physics on the one hand and astrophysics and cosmology on the other hand, helping us to, as I already mentioned, answer Gauguin's questions. Now, I think it's perhaps useful to remember that particle physics, although it seems to be very different from astrophysics and cosmology, actually many of the early discoveries in particle physics were made using studies of cosmic rays. So cosmic rays, these are energetic particles or nuclei that hit the upper atmosphere. They're produced by explosions in space. When these energetic particles hit the atmosphere, their energy is converted into other particles, and many new particles were discovered by looking at those showers produced by the cosmic rays. So I'm thinking, for example, of antimatter. The positron was first discovered in cosmic rays, the muon, and other heavier particles. But it's difficult to study these particles in detail when you've got this sort of random source of particles from heaven knows where, with goodness knows what energies appearing at random times. And so that's why particle physicists in the middle of the last century started building accelerators so that they could study the collisions of these energetic particles directly under controlled conditions in the laboratory. And that enabled physicists to study their properties in detail. So these particle accelerators, in particular the modern generations of accelerators where we collide particles, are what one might regard as super microscopes capable of probing very short distances, looking, as I already mentioned, deep inside the atom, the nucleus, and elementary particles. So here's a sort of generic picture of what an experimental apparatus looks like. So particles are collided along the horizontal axis, and around the collision points you have detectors which are designed basically like sort of cylindrical onions with different layers that detect different types of particle coming out. And as I already mentioned, these collisions reproduce the conditions which held in the first fraction of a second after the Big Bang. So what have those studies revealed so far? So they have established what we call somewhat modestly the standard model of particle physics. This is a theory that was proposed by Abdus Salam, whom you see at the top there, from Pakistan, and two American theorists, Glashow and Weinberg, in the 1960s. And an essential element in their theory was the suggestion by Peter Higgs of the Higgs boson, which I will come back to in a moment. Now, for quite some years after they proposed their theory, people didn't pay a lot of attention. But that changed in the early 1970s when experiments, particularly at CERN, discovered some new phenomena which were predicted by the standard model. Subsequently, in the 1980s, 1990s, more aspects of the standard model predictions were verified by experiment. In particular, there were experiments at CERN in the 1990s that verified many of the predictions with a precision well below the percent level. So if you look at that picture over there, you can see a green curve. That's a theoretical prediction. And you can see little red dots. Those are experimental measurements. And you can see there's excellent agreement. In fact, that's a bit of a cheat, because the red dot has been expanded by a factor of 10 so that you can see it. That's just telling you how accurately the standard model works. So what does this standard model contain? So it contains particles of matter, some of which I've already mentioned, like the electron that we've all heard about. Over on the left-hand side of this picture, we have the quarks, which make up nuclear particles. There's 6 of them. There's a heavier electron-like particle called the muon, another one called the tau, and there are also neutrinos. I won't say very much about neutrinos, but happy to answer questions if there are some about neutrinos at the end. So we distinguish 4 fundamental forces acting in between these particles. 2 of them are very familiar. There's gravitation and there's electromagnetism. 2 of them are perhaps less familiar. One is the strong nuclear force that holds protons and neutrons together in nuclei, and in fact holds quarks together inside protons and neutrons. And that's the force that's carried by the gluon particle that Marta mentioned in the introduction. There is, in addition, a weak force that acts at the level of particles and nuclei, which you see there with a big W. W because it's mediated by a particle, which we call the W, which is a very, if you like, weighty particle. It weighs as much as a medium-sized nucleus. Which, of course, raises a question. Where did the mass of that W particle come from? And also, where do the masses of other particles come from? Like, for example, the electron up there. If the electron didn't have a mass, then it would always travel at the speed of light, and it would never stay around to bind to a nucleus to make an atom. And neither we nor Albert Einstein could exist. So it's essential to understand what is the origin of particle masses, and that is where Peter Higgs comes in. So you may dimly remember from high school physics that Newton taught us that weight is proportional to mass. So you probably think, well, Newton must have understood what mass was. But no, he didn't. Einstein told us that E is equal to mc squared. Energy is related to mass. So did he understand where mass came from? He didn't either. And here we have Peter Higgs. And behind him we have a blackboard with his theory written on it. And so that you won't forget the theory, I have it on my t-shirt. So sensitive spirits, don't worry, I'm not going to go to another layer below the t-shirt. Okay, so this formula here represents mathematically the standard model that I'm talking about, including, in particular, the Higgs boson, which I'm going to be discussing in a bit more detail now. So the Higgs boson was proposed by Peter Higgs in 1964, but it took 48 years to discover it. So I'm not going to describe in detail the mathematics of the theory, and don't worry, there won't be an exam at the end of the lecture. But I will give you an analogy which may help you understand how the Higgs idea works. So the idea is that you should imagine space as containing a universal medium. So this is what in particle physics we call a field. You may have heard of some fields. You've heard of the electromagnetic field, you've heard of the gravitational field. These all are generated by sources like electric charges or a planet, for example. The Higgs field is somewhat different. As far as we can tell, it is homogeneous, isotropic, and it's been essentially constant all the way back to a very short period after the Big Bang. So how can we imagine it? So the analogy that I propose is that we're in Siberia in the middle of winter, and there is a snow field as far as the eye can see in every direction. Uniform, featureless. So let's imagine that we're trying to go through that Siberian snow field, the analogy with a particle trying to go through the Higgs field. So if we have skis, we go through very quickly. We don't sink into the snow. That's like a particle that doesn't interact with the Higgs snow field. And if it doesn't interact with the Higgs snow field, according to the theory, it has no mass, it travels at the speed of light, it travels very fast, by analogy with a skier. Or perhaps we don't have skis, we have snowshoes. Well, in that case, we're going to sink into the snow, and that's like a particle that interacts with the Higgs field. You travel slower than the skier. It's like a particle that travels slower than the photon, a particle with mass, the electron maybe. And then finally, maybe you don't have any snow equipment at all. So in that case, you're going to move very slowly through that snow field. You interact very strongly with the Higgs field. That's like a particle with a very large mass. So that's the basic idea. A universal medium, and the mass of a particle depends on how strongly it interacts with this universal field. What about the Higgs boson? Well, what is a snow field made of? It's made of snowflakes. And in the same way, you can imagine that this universal Higgs field has an associated, what we call a quantum. The electromagnetic field has a quantum, which is called the photon. The Higgs field has a quantum that we call the Higgs boson. And what the LHC experiments did in 2012 was to discover this snowflake. And we're still trying to understand it. So, for example, one of the big discussions that's still taking place is how far can you push this flaky analogy? So, of course, there's many different sizes and shapes for snowflakes. And that's possible because snowflakes are composite objects made up out of water molecules arranged in different ways. So maybe in the same way, the Higgs boson is made up out of smaller constituents, and maybe if you arrange them in different ways, you get other Higgs-like particles. And that's something which the LHC experiments are still trying to understand. So I've actually been trying to understand the Higgs boson since 1965, when together with Mary Gaillard and Dimitri Nanopoulos, we wrote a paper about how the Higgs might show up in experiments. Now, at the time, these ideas that I've been describing were regarded by the distinguished grey-haired professors as being very speculative. And so we were very careful when we wrote our paper. We said, we don't want to encourage big experimental searches for the Higgs boson, but we do feel that people doing experiments should know what the Higgs boson might look like. So fortunately, our experimental colleagues didn't take our bad advice, and they built experiments at the Large Hadron Collider to answer Gauguin's questions in general, and specifically to look for the Higgs boson, but also other Gauguin questions, as I'll discuss in a moment. So, Large Hadron Collider. Let's unpack that name. Large, because it's 27 kilometers in circumference. Collider, I already explained. Hadron, that's our jargon term for a strongly interacting particle that has nuclear interactions. So in this picture here, you are in the tunnel where the accelerator is located. It's on average about 100 meters underground. And the particles go around in circles in opposite directions, guided by magnets which are sitting in those blue tubes there. So when it's in operation, you've got thousands of billions of protons going in each direction. Each one has approximately the energy of a fly, and they make billions of collisions per second. And what we hope to find in those collisions is an explanation for the origin of mass, for the nature of dark matter, the nature of the primordial plasma that filled the universe when it was very young, and we study the difference between matter and antimatter that might be linked to the origin of matter in the universe. So I talked earlier on about particle physics experiments being like cylindrical onions. Well, big onions. So the biggest of the LHC experiments is the one called Atlas in the top right. It's about 50 meters long, about 25 meters in diameter. It and its friendly rival CMS, bottom left, were designed to look for the Higgs boson, dark matter, and other new particles. Top left, we have Ellis, whose main job is to look at the primordial plasma. And bottom right, we have the LHCb experiment trying to understand the difference between matter and antimatter, and perhaps the origin of matter in the universe. So you can judge the size of Atlas by noticing there's a very small person just above and. Okay. And you also notice that there is a UAE flag, because now there is a team from NYUAD and from the University of Sharjah and UAEU that is working together on the Atlas experiment. So that's just one aspect of something that I would like to underline, that the experiments at CERN are done by scientists from around the world. And this reflects the fact that, if you like, our quest is a universal quest. Everybody is asking the same questions. Although discoveries like the Higgs boson are made at CERN, they're not made by CERN. They're made by these big international teams, now including, as I've emphasized, scientists from the UAE. Just a small aside. You will see in this picture some countries are colored dark blue. Those are the member states of CERN. Some countries are colored light blue. Those are associate members. Some countries are colored green, like Russia. That's an observer state at CERN. And some others are red. Those are countries which are not formally members of CERN, but we do have cooperation agreements with them, and that includes the UAE. Ukraine, you will notice, is light blue. So back in the 1990s, there was a very interesting development at CERN, which was cartridges from the Russian Navy were melted down to make components for the CMS experiment. And this here shows you some of the Russian workers who were working on that process, financed largely by the United States, and then the brass was then machined in Belarus. That was obviously a different time from the one that we're living through right now. Okay, now I want to talk about the discovery of the Higgs boson back in 2012. And I like to describe the reaction of particle physicists to this discovery as being mass Higgsteria. So this was triggered by the observation by both Atlas and CMS experiments of interesting events which corresponded to perhaps the production of a Higgs boson and its subsequent decay. So here is a computer reconstruction of the Atlas experiment. And you can see coming out of the collision curved yellow lines. Those are charged particles being bent in the magnetic field. You can see blobs disembodied, which represent neutral particles hitting outer parts of the detector. And you can see 4 almost straight red lines. And those are thought to have been muons that were produced very likely in the decay of a Higgs boson. This is a corresponding picture from the CMS experiment. Here you see, again, those yellow curved charged particles. You also see 2 long red towers, which are deposits of energy, presumably, probably, by photons, which might have come from the decay of a Higgs boson. And that was a process that we calculated back in 1975. Now, if you just see 1 or 2 events of this type, you can't be sure that you've discovered a Higgs boson, because every once in a while, those things happen also with other standard model processes. But eventually, on July the 4th, 2012, what we call Higgs Dependence Day, the Atlas and CMS experiments announced that they had discovered sufficiently many of these events to be sure that they had discovered a new particle. And this is the scene in the CERN auditorium that day. And in the front, you've got a lot of former directors general of CERN, but I would draw your attention to the guy with his back to you. Now, he's the really important guy. That's Lynn Evans, who directed the construction of the accelerator. So this is a picture which I like, because on the right you have Peter Higgs. And in the middle you have François Englert, who proposed similar ideas back in 1964 independently, although he didn't predict the existence of the Higgs boson. And although they proposed these ideas 48 years previously, somehow they had avoided meeting each other for 48 years. And this is the moment when they met. So that's one reason why I like that picture. The other reason is because it shows Fabiola Gianotti, who announced the discovery on behalf of the Atlas experiment, and now is the Director General of CERN, proving that there's no glass ceiling. And she has a hell of a job. Quite apart from the physics, she's had to deal with COVID, and now she's got to deal with Russia. So I don't envy her. Okay, so what happened on July the 4th was that a new particle was discovered. But was this really the Higgs boson that the experiments were looking for? So I sort of draw an analogy with when you're doing a jigsaw puzzle and there's one piece missing. Where's it gone? And finally, in the back of the sofa, you find a bit of bent cardboard with a picture rubbed off. Does it have the right size and shape to complete the puzzle? So that was the theme of much research in the years following the discovery of the new particle. And I worked on this together with my then PhD student, Tivong Yu. And we particularly addressed the question, are the couplings of this particle to other particles proportional to their mass? So since the Higgs gives masses to those particles, its coupling, its connection to those particles should be proportional to the mass. And here you see that within uncertainties it is, the mass is on the horizontal axis and the coupling is on the vertical axis. So we wrote in our paper that it walks and quacks like a Higgs boson. Subsequently, this type of analysis has been done much more precisely, much more professionally, with much more data by the Atlas and CMS experiments, and it still remains true that the measured couplings of the Higgs boson are in very good agreement with the standard model predictions. So it's not surprising that in 2013, the Nobel Prize Committee rewarded Peter Higgs and François Englert, and they wrote in their citation, "Today we believe that without any doubt it is a Higgs boson." And my student and I were very pleased because that quotation was taken directly from our paper. But what the Nobel Prize Committee did not know was that when we sent our paper to a journal for publication, the referee said, "No, beyond any reasonable doubt is not a scientific judgment. You have to take that phrase out of your paper." So, not good enough for the referee, but good enough for the Nobel Prize Committee. So, the discovery of the Higgs boson was a big deal. Without it, there'd be no atoms, electrons would run away from nuclei at the speed of light, there'd be no heavy nuclei, weak interactions would not be weak, life would be impossible. Its discovery was indeed a big deal. So what has that got to do with James Bond? Well, of course, you have to change things a little bit. Those of you who've seen the movie may remember that the lady on the left was the villain of the movie, but I assure you that Fabiola is no villain. So I paraphrase the title of the movie, and I claim the standard model is not enough. And in reference to James Bond, I give you 007 reasons for claiming that. So one of them is that the measurements at the LHC indicate that very possibly empty space is unstable. I'll explain that in a moment. The standard model does not contain a candidate for dark matter. It doesn't explain the origin of matter. It doesn't explain the masses and mixing that we see for neutrinos. There are many other problems as well. I won't go through the details of them. What I will do is I will discuss, at least briefly, these three questions, which can be related directly to the Gauguin questions that I asked at the beginning. What is the nature of dark matter? Where do we come from? What's the origin of matter? And what is the future? Is it really true that empty space is unstable and that the universe is doomed to collapse? And these are all questions that the LHC is now addressing. So, will the universe collapse? So in this picture here, you have to imagine the depth or the strength of the Higgs field going from left to right. So we are represented by that red dot, where there's a small, not very large value of the Higgs field. But measurements of the mass of the Higgs boson and other particles at the LHC indicate that there may be another very dense configuration of the Higgs field over there on the right-hand side. And if we were in that state, then the universe would collapse. So this is where we start worrying about Gauguin's third question. We worry in particular because, like everything else, the Higgs field is subject to quantum fluctuations. And those quantum fluctuations could cause our universe to tunnel through that barrier and into that ultra-dense big crunch state. Don't worry, it's not going to happen soon. We'll probably have to wait for 10 to the 100 or 10 to the 1,000 years, but it's a matter of principle. But there's another aspect to this problem, which goes back to the other Gauguin question: where do we come from? How on earth is it that we got to be over there on the left now and not over there on the right? And this is an issue because early in the history of the universe, those quantum fluctuations would have been much larger. And by rights, essentially all the universe should have jumped over the barrier and into that big crunch state. So how can this be avoided? Well, one way to avoid it is to follow the advice of President Trump and build a wall, illustrated by that straight line there. And that you can do in various extensions of the standard model. For example, supersymmetry. Supersymmetry would mean that there would be no big crunch. But I'll come back to the theory of supersymmetry a little bit later on. It's about time, I think, that I actually discussed the dark matter hypothesis in a bit more detail. So this was proposed by the Swiss astronomer Fritz Zwicky in the 1930s, and it was motivated by his observations of the Coma cluster of galaxies. So these galaxies are moving around each other fast, faster than you'd expect if they were held in place by the gravitational field generated by the galaxies themselves. There would have to be some additional gravitational field to hold the coma cluster together. And this additional gravitational field, he postulated, would be produced by some invisible dark matter. I think it wasn't until the 1970s that people started becoming convinced by Fritz Zwickie's proposal. And a lot of the credit for convincing astrophysicists goes to Vera Rubin, whom you see in this picture here. She observed stars moving around galaxies. And she found the same thing. Those stars orbit too quickly. Hers and other observations also required a stronger gravitational field around that galaxy than was provided by the visible matter. So this is further strong evidence for dark matter, and by now there's many, many other indicators, for example, on the formation of structures in the universe, the cosmic microwave, but lots of pieces of evidence for dark matter. But let me just show you the sort of observation that Vera Rubin made back in the 1970s. So the horizontal axis here is the radial distance from the center of a galaxy, shown over there on the left-hand side. And you see various lines there corresponding to the orbital velocities that you would expect based on the gravitational field generated by the visible stars, by the gas, and the orbital velocities that you actually observe, which are much larger and essentially constant, going out to very large radii. So that higher velocity would have to be generated by a higher gravitational field, such as generated by a dark matter halo. So what could that dark matter be? So the favorite hypothesis is that it's some sort of unknown particle beyond the standard model. There's no standard model candidate. One possibility is supersymmetry. Supersymmetry is a theory that predicts that all the known particles have partners which have similar internal properties like electric charge, but different masses, and they spin in a different way. And the lightest of those supersymmetric particles in many models are stable, and they could be around in the universe today making up the dark matter, and they could be produced at the LHC. So here I've taken the standard model particles that we met close to the beginning of the talk, and I show on the right-hand side their supersymmetric partners, which, as I said, had the similar internal properties, but different masses. And here I've highlighted in black the possible candidates for dark matter. So how would we look for dark matter at the LHC? Well, it's difficult because they're dark. They don't have an electric charge. They don't have strong interactions. Typically, they would just escape from any collision that made them. But what they would do would be to carry away with them energy and momentum. So what ATLAS and CMS set out to do was to look for events where there was missing momentum being carried out of the detector on one side. And that's a computer reconstruction which illustrates the principle. It's a bunch of energetic particles coming out bottom right, but nothing to balance them going up top left. So far, no excess of such events has been seen. I should add that experiments, of course, are looking for a whole bunch of other possible phenomena beyond the standard model. Haven't had any luck with them either. And I think one of the questions that experimentalists at the LHC are now wondering is, should they keep on looking in the same way, or should they maybe look for some sorts of novel signatures? And that's going to be one of the main topics in the next run of the LHC, which is supposed to start in a few weeks' time. Now, another way of looking for dark matter is to look directly for the scattering of dark matter particles in the laboratory. But not just any laboratory. You have to go deep underground so as to protect yourself from cosmic rays, and you have to shield your detector so that you don't get confused by radioactivity. And there's a team here at NYUAD which is working on one of the leading deep underground experiments looking for dark matter. Have you found anything yet? Not yet. Okay. Still looking. Where do we come from? So I talked a little bit at the beginning about antimatter, and I mentioned that there's a dedicated experiment at the LHC trying to understand the difference that exists between matter and antimatter. So, you know, the general public, when they hear about antimatter, they start thinking about Star Trek or angels and demons, but I can assure you we don't make enough antimatter to blow up the Vatican. Not, of course, that we would want to in any case. So, as I already said, our key interest is to try to understand how matter and antimatter differ. So the existence of antimatter was postulated by Dirac in the 1920s when he wrote down an equation that combined quantum mechanics with special relativity. He said there should be these other particles with the same masses as regular particles, but opposite internal properties such as electric charge. As I already mentioned, the first antimatter particles were discovered in the cosmic rays, then they were studied in great detail in accelerators, and they're now used in medical diagnosis in so-called positron emission tomography scanners, which are used to diagnose thousands of patients around the world every year. Now, it came as a big surprise when people realized that the interactions of matter and antimatter particles are not quite equal and opposite. And it was suggested by the Russian physicist Sakharov that this could explain why it is that the universe contains blobs of matter, like you, but no anti-U's, no blobs of antimatter. So Sakharov came to CERN in around 1990. Here he is visiting one of the experiments. So he said, well, look, we know that there is a difference between matter and antimatter observed in the laboratory. We believe that there are interactions which can create matter, although they haven't yet been observed. And we know the universe is expanding. And during that expansion, those matter-antimatter differences could act as levers to generate more matter than antimatter in the universe, and then eventually the matter would dominate as we see today. So, as I mentioned already, there is one dedicated LHC experiment trying to look at these matter-antimatter differences. And in fact, just today, they published a paper showing a whole bunch of new matter-antimatter differences for us theorists to chew on. That pretty much brings me to the end of my talk, but I can't resist returning to Einstein, a little bit older here than in the earlier picture, maybe looking a little bit sad, because maybe he had a premonition that he was not going to succeed in constructing a unified theory of all the fundamental interactions. Now, one of the ideas that he worked on was the idea that interactions might be unified in additional dimensions of space. And that's something that's become very fashionable in the last 30 or 40 years in a context of string theory that you may have heard about. Now, in some of these theories with extra dimensions, gravity would become strong at the LHC, in which case the LHC experiments might create microscopic black holes. These would not eat up the Earth. They would vanish, essentially instantaneously. But if they existed, they would be a fantastic laboratory for studying some of the deepest problems in theoretical physics, quantum mechanics of black holes. Unfortunately, the LHC has not yet observed any black holes, but I guess you're still looking. So that brings me to the end of my talk. I hope I've convinced you that the LHC at CERN is the world's most powerful microscope so far. But hopefully I've also convinced you that it is also, in some sense, a telescope which addresses Gauguin's fundamental questions.